Hi. It's my pleasure to introduce Dr. Elizabeth Cottrell. Liz Cottrell received her Bachelor of Science degree in geochemistry from Brown University before spending a year in Paris, France, as a Fulbright scholar at l'Institut de Physique de Globe. She went on to earn her PhD from Columbia University Lamont Doherty Earth Observatory, and following a postdoctoral fellowship at Carnegie's Geophysical Laboratory, joined the Department of Mineral Science at the Smithsonian National Museum of Natural History. Today, Liz serves as the chair of the Department of Mineral Sciences, where she also curates the National Rock and Ore Collection. Her work has been widely recognized across the geochemical community. She is a fellow of the Mineralogical Society of America and a geochemistry fellow of both the International Geochemical Society and the European Association for Geochemistry. This year, she is also being honored by the European Association for Geochemistry with the 10 Ringwood Science Innovation Award Medal. Please join me in welcoming Dr. Elizabeth Cottrell. Liz, the floor is yours.
Hi, thank you so much, James. I'm on a different, I just had to switch computers here, but sounds like, James, just give me a thumbs up. The audio is okay and the video. Okay, excellent. All right, this is an opportunity to have a conversation. Feel free to unmute yourself, interrupt. If anything is unclear, you want to interject a question. I don't think you need to hold your questions to the end, although I think there will be time for questions at the end. So I want to chat today about Earth's past and present mantle redox and focusing really on the past. This is the Precambrian seminar. I want to start out just acknowledging collaborators. A lot of what I'm presenting today recently was presented in a Nature Reviews Earth and Environmental Sciences article with co-authors Dante Keneal, Katie Evans, Charlie Langmuir, and Fabrice Gaillard. But there's a lot of input and formative conversations with Suzanne Berner, who was honored last year with the Clark Medal for some of the work I'll be sharing today, and Fred Davis and Jessica Warren. But mostly focused on this review paper. Although this first image that I'm showing here is from the Berner study. We're looking here at a thin section of peridotite dredged from the Gackle Ridge, and you can see the minerals here in thin section are olivine, orthopyroxene, and spinel, and that mineral assemblage allows us to analyze the minerals and constrain the oxygen fugacity that this rock is recording, its equilibrium oxygen fugacity. And that's what the presentation will be about today. Okay, advance my slides here. So this is not a redox crowd necessarily, so I just want to introduce the concept of oxygen fugacity. We're all breathing air. Air can be approximated as an ideal gas, and the concentration of oxygen in air is about 0.21 mole percent. And so it's easy to make the leap from concentration of oxygen in the air to partial pressure. So the concentration is 21 mole percent, the partial pressure is 0.21, and the oxygen fugacity is 0.21. I think I start the talk this way to immediately help the audience to make the uncomfortable disconnection between concentration and chemical activity. The mantle has about 3 times more oxygen than air. The concentration of oxygen in the mantle is about 58 mole percent, and yet the oxygen fugacity, the effective concentration of that oxygen, is many, many orders of magnitude, about 7 orders of magnitude lower than it is in air. That oxygen is not chemically available to drive redox reactions the way it is in air. So while we have a much higher concentration of oxygen, its chemical activity is lower. And this is the kind of the fundamental thing that makes redox tricky, I think, especially for geochemists who and isotope geochemists who like to count atoms, who like to count concentration. That intuition fails you when it comes to thermodynamics. I don't want to go into the thermo too much for what I'll be showing today, but we are going to be talking about oxygen fugacity relative to some standard solid state reactions. On the y-axis here, I have oxygen fugacity, and on the x-axis is temperature. And we can just take one of these two reaction lines, the equilibrium between iron and iron oxide, or the equilibrium between hematite and magnetite. Those reactions have a temperature dependence. And so anywhere that we're along, for example, this black curve, anywhere we are along the curve, where iron and wustite are in equilibrium, we've constrained the oxygen fugacity so long as we specify the temperature. The one most commonly employed, although it's not always the best choice, what is most commonly employed by petrologists is the quartz phalite magnetite buffer. Again, not meaning that there's quartz, phalite, and magnetite minerals in our system. It's just a reference state that defines the oxygen fugacity as a function of temperature. So we're usually going to talk in log units above or below this buffer curve or other buffer curves. Now, behind this reaction is thermodynamics, and I just have to move my Zoom thing there. Okay. Is this thermodynamics that allows us to relate the free energy of the reaction to the oxygen fugacity. We have oxygen as a pure phase on one side of the reaction here. What I want to make the important distinction here is between the oxygen fugacity and the redox budget. So we're talking about this reaction here where we have quartz, phalite, and magnetite in equilibrium. Let's imagine that we have a mole of each of those minerals. Phalite is the iron 2 plus rich end member for olivine. Magnetite is ferric rich spinel. Now imagine we take and we make 10 moles of spinel, 1 mole of olivine, 1 mole of quartz. We've increased the redox budget. We've increased the ratio of ferric iron to ferrous iron in this rock by a lot. But if we were to melt this rock, it would have the same 3 plus to total ratio in the melt and the same oxygen fugacity. This assemblage has imposes the same oxygen fugacity, even if there's, whether there's 10 times more or less magnetite, because it's the reaction buffering the FO2. Now, what if we remove that last crystal of olivine, that last crystal of phalite? Well, we haven't really changed the redox budget very much. It's nearly identical. But the melt that would be in equilibrium with an assemblage of just quartz and magnetite would have a higher 3 plus to total ratio, would have a higher oxygen fugacity, even though the redox budget hasn't changed. So again, we have to disconnect the ratio of heterovalent species, say ferric iron to ferrous iron, from oxygen fugacity. So if I get one thing across in this talk, it would be that when you're reading papers about redox in the Archaean, Mantle redox, any kind of system redox, ask yourself, when someone says something is more oxidized or more reduced, do they mean that it has a higher redox budget, that its bulk, say ferric ferrous ratio is higher? Or do they mean that the oxygen fugacity of the system is higher? And those could be two really different answers. So let's keep this thermo question and this redox budget question in mind. Okay, so the activity of iron in solid earth minerals controls oxygen fugacity. So in the earth, in the mantle, it's going to be the activity of ferric iron in minerals that's going to control our oxygen fugacity. And then trace elements such as vanadium are going to change their oxidation state in response to the oxygen fugacity imposed by the system. Okay, why should you care about oxygen fugacity? Obviously, this group cares somewhat, or you wouldn't have invited me to speak here today. Generally, though, I think we know that it's important for the generation of ores, the formation of continental crust. So the continents generally have more oxidized rocks than, for example, the seafloor. It's important for mass transfer at subduction zones, transferring redox-sensitive species from the mantle to the crust and concentrating them as ores. And these are just, here's an example from this recent review where we're recasting FO2 in terms of, again, redox budget. What is coming down through the subduction zone? What fluids, melts, or bulk mixing has the potential to change the redox budget of the system? What mass transfer process? The other reason to care about oxygen fugacity, which is particularly relevant for a conversation about the Archaean, is the depth of incipient melting. We've known, since the 70s that carbonate lowers the melting point of peridotite, just as water does. But it's a little bit different in the case of carbon because when you're under more reducing conditions and the carbon is present as graphite or diamond, it does not flux melting. So melting of the mantle, those initial melts, the depth of melting is going to be redox sensitive. And that's illustrated here. This is a modification from Stanio et al. In Nature in 2013, really a classic paper, where what they're showing here is the y-axis is oxygen fugacity and the x-axis is depth. So you can see the graphite diamond transition there, which is occurring at a given depth. You have this orange isopleth, which is the equilibrium between olivine, orthopyroxene, and garnet. And so for a fixed bulk 3+ to total ratio for the mantle, in this case, I'm showing a 3+ to total ratio of 0.03 for the bulk mantle. That's a very commonly invoked ratio, 0.03. The mantle at constant 3+ to total gets more reduced with depth in the garnet field. So that's what you're seeing here. You're seeing, if you follow this orange line, this isopleth, it's more reduced the deeper you go in the earth. The oxygen fugacity, and when I say reduced, the oxygen fugacity is lower, even though the bulk composition is staying the same. Again, this is an essential concept. As you get shallower and you cross the oxygen fugacity necessary to convert graphite to carbonate, which is represented by this somewhat horizontal teal line, you initiate melting because the carbonate will begin to flux melting in the mantle. If we were on a different isopleth, and here I've doubled the ferric to total ratio to 0.06, we would intersect that reaction boundary deeper and we would begin melting deeper. Okay, so this has large geophysical implications. It would have implications for the history of melting in Earth's mantle. And I think what we've seen in this field in the last 5 years is a much broader discussion and a much richer discussion about the interplay between temperature, pressure, mantle mineral assemblage, and oxygen fugacity and redox. Finally, and also important to a conversation about the Archaean, is that if the Earth's atmosphere has outgassed from the mantle, the composition of Earth's initial and subsequent atmospheres will have been dependent on the oxygen fugacity imposed at the surface of a magma ocean, and later by the mantle. Oxygen fugacity in that mantle will initiate the phase stability in the mantle. The 3+ to total ratio of that magma ocean will set the phase assemblage of the mantle, and thereby the compositions of the earliest planetary crusts will also depend on what comes down to the 3+ to total ratio of the mantle. And we know, if we go back to accretion and core formation, that the equilibration of metal and silicate at low pressures enforces a liquid oxygen fugacity, a system oxygen fugacity that's at least 5 orders of magnitude lower than the mantle is at now. Okay, so during core formation, especially in a small planetary body, very reducing conditions as metal separated from silicate. So that's the initial condition. And today we have something else. How did that happen and when? Okay, and this is just a nice figure from Fabrice Gaillard's review paper from 2021 showing oxygen fugacity on the x-axis and abundance on the y-axis, just showing that under reducing conditions, we would have a hydrogen atmosphere. Under more oxidizing conditions, a water CO2 rich atmosphere. Exactly what I just said. Okay, so how are we going to assess oxygen fugacity? Historically, the most ways that have been around since for decades, magnetite-ilmenite pairs, for example, in a volcanic rock. You can measure the compositions of magnetite and ilmenite in equilibrium. We already talked about the hematite-magnetite buffer, and you can calculate an oxygen fugacity. You can look at spinel, olivine, orthopyroxene. There's a mantle assemblage that you can use to calculate the oxygen fugacity recorded by that rock. You can also, if you have glass with the 3+ to total ratio, relate that empirically to the oxygen fugacity because you don't have to worry about crystal chemical constraints on minerals. And we'll also talk today about redox-sensitive trace element ratios, which you can relate to an oxygen fugacity, not through oxybarometry, but you need a model to go between the oxidation state of a heterovalent trace element or its concentration to the oxygen fugacity of the petrological system from which that trace element is coming. Okay, so I like this figure, kind of compiles, I believe, currently, I think this is current as of today, oxybarometric measurement of basalts and peridotites that are published in the literature. The circles are basalts, the stars are peridotites, and the color bar on this map represents the oxygen fugacity from that oxybarometry. And what you can see is that mid-ocean ridges, the basalts erupted at mid-ocean ridges record oxygen fugacities at about QFM. And basalts erupted at arcs record oxygen fugacities that are 1 to 2 orders of magnitude higher. And we see this in arc xenoliths and in the peridotites exhumed as arc xenoliths, and we see this same dichotomy in seafloor peridotites, ridge peridotites, where the ridges are more reduced than arc environments. And this has to do with, it must come back to redox budget transfer happening in subduction zones. So I raise this because this is a modern snapshot. Okay, and if we don't understand where we are today and have a good sense of, what are the error bars on our oxybarometry, I will tell you that if you measure the 3+ to total ratio of a glass, you're only going to be able to know the oxygen fugacity of that glass to within about half a log unit. Okay, that's with like perfect knowledge of a 3+ to total ratio that you get from a glass you quenched in a 1 atmosphere furnace where the oxygen fugacity is known. And you do that a bunch of times and you look at these empirical relationships. The precision on this is about half a log unit in oxygen fugacity. And with spinel peridotites, when we're looking at assemblages, again, we equilibrate an assemblage in a furnace or in an experiment. We measure the phases. We still are only going to know those oxygen fugacities to within half a log unit to a log unit. Okay, so we do not have infinite precision even when we have 100% information. That's the modern view. Okay, going back in time, this graph will become of no surprise to this crowd. We're now looking at oxygen on Earth in the atmosphere as a function of time. Early in Earth's history, no oxygen in the atmosphere, and now we have an oxygenated atmosphere. The moment of this oxygen rise has been termed the Great Oxidation event. Obviously, incredibly important event in the history of Earth. And I think the big question that this community has been asking is, what, if anything, did the mantle, Earth's mantle, solid Earth, have to do with this shift? Did any evolution in the mantle Did the mantle respond to this shift in the atmosphere? Did shifts in the mantle either trigger or allow this shift to take place in the atmosphere? So here's a figure that's been modified from O'Neill and Albach that summarizes a bunch of work from a bunch of different labs, several papers from Nicholas et al. And Albach and Stanio, Albach et al., showing data from metabasalts and komatiites through time. And I've taken the original figure from the paper and just flipped it left to right to match the age progression from the upper figure. And you can see the data on this slide, and they've superimposed an arc of evolution, implying oxidation of the mantle now, and the suggestion that there was a shift in the volcanic gas composition, the GOE, and the message is that the shifts in the solid Earth triggered or at least enabled the great oxidation event to take place, that there's a timing here that is relevant. And so that's what I want to interrogate a little bit in this talk. Okay, so what are some of these data based on? It's based on vanadium. Vanadium's multivalent. It can exist in 2+, 3+, 4+, 5+ valence states over a range of Earth-relevant oxygen fugacities, and its geochemical behavior is therefore sensitive to oxygen fugacity because it can, when it changes valence state, its compatibility during mantle melting changes. Its ability to fit into crystal structures changes. So vanadium 5+ and 4+ are more highly incompatible than vanadium 3+ in, for example, olivine. Vanadium 3+, vanadium's always incompatible in olivine, but under oxidizing conditions, vanadium's even more incompatible. This came from the paradigm shifting paper of Dante Keneal in Nature in 1997, where he performed experiments at 1 atmosphere, where he, on the y-axis now, we're looking at the partition coefficient of vanadium between olivine and liquid. And on the x-axis, we're looking at oxygen fugacity. Now, the buffer here is nickel-nickel oxide, and I've kind of made a mini scale of QFM, just so we keep the whole talk in one buffer reference frame on the x-axis. So the oxygen fugacity calculated from an olivine melt pair using this calibration, which is done in a 1 atmosphere furnace in a lab, has a precision, again, 0.5 log units, right? That's what the paper says, 0.5 log units. And you can see he investigated many different temperatures, 1200, 1300, 1400 degrees, and there is no temperature dependence. There is a recent paper, there was no temperature dependence in this data set. If you look at 1 atmosphere data across many studies, very carefully done over decades, you see no temperature dependence or a minor temperature dependence to vanadium partitioning. When you ratio vanadium to scandium, then there truly is no temperature dependence at all visible in these very well-constrained 1 atmosphere experiments where we can precisely control the oxygen fugacity. There's no temperature dependence, so we don't need to worry about that. Okay, so temperature dependence aside, what Dante did in 1997 is he had this calibration, and then he looked at glass olivine pairs in natural komatiites, okay, and measured how vanadium partitioned between olivine and liquid, and then took that value, okay, by analyzing vanadium in the glass and analyzing vanadium in the olivine, and compared that to his calibration, and concluded that the vanadium partitioning in those komatiite flows was consistent with oxygen fugacities that were greater than QFM, okay, greater than modern mid-ocean ridge basalts. And he looked at 6 different komatiite flows, okay, number of localities, and they all recorded oxygen fugacities from QFM -1 to QFM +2. He estimated that the precision on any given flow was about 1 log unit. And again, modern mid-ocean ridge basalts, as we established earlier in the talk, record about QFM. Okay, so he concluded in 1997 that the Archaean mantle records oxygen fugacity indistinguishable from modern MORB. And this was really paradigm shifting at the time. I was a graduate student when this paper came out, or I was a first year graduate student in 1998 when this paper had just come out. And it was a huge deal at the time because everyone knew that core formation had to have taken place, below the iron wüstite buffer, 5 orders of magnitude below where we are now. There was a conceptual model of the Earth's mantle oxidizing through time. So it was truly seminal and paradigm shifting when this study came out and said, actually, it looks like the rock record is telling us that the Archaean mantle was already oxidized. Okay, what's happening now today in our modern community? A lot of great measurements coming out of the Nicholas group. Here's measurements from 2016, 2018, 2019. On komatiite pickrite lavas. And this is now a different technique. This is a model. This is not measuring vanadium in glass olivine pairs. This is measuring vanadium in just the olivine and using a model to infer the glass. And the Nicholas et al., the 2022 paper is the paper that best describes the step-by-step method that they're using to arrive at these oxygen fugacities from the vanadium concentrations. And the interpretation here, and these data are included in that O'Neill and Albach review that I showed earlier. And the interpretation of these data is that you have oxidation through time recorded by these komatiites. And then there's an outlier back in the oldest flow there. I'm adding to this now olivine glass pairs many times from these exact same flows from other studies where they've measured vanadium in the glass and the olivine to get the oxygen fugacity from that Cottrell approach, again in the same flows. And you can see sometimes there's some overlap and sometimes there's not overlap. Those white hexagons are the averages of many inclusion glass pairs. So you can get a sense of the precision again on this. But what I think is most interesting is that if we look at mid-ocean ridge basalts, that I'm now showing the data from Nicholas et al. 2022A, 2022B, and 2024, where they've applied the exact same technique as is applied to these komatiite flows to modern mid-ocean ridge basalts dredged today, zero age MORB, are shown as the blue stars. And these little white diamonds are ocean island basalts. These are olivines from ocean island basalts today. And then using the exact same method as described in 2022, which is the same method as applied to the komatiites, this is the range that we get today. So the range of modern MORB with this technique spans from just below QFM to QFM plus 1, 1.25. And ocean island basalts using this technique span from QFM up to QFM plus, going over QFM plus 2, so QFM plus 2.25. And we know from looking at the 3+ to total ratios of glass, okay, we have, there's literally hundreds of measurements of this now, and the histogram is very, very tight, clustered around 0. So the 3+ to total ratio, ferric-ferrous ratio in mid-ocean ridge basalts records QFM, very tight. And so when I look at this, I see that this method of relating vanadium in olivine to FO2 just paints a very wide swath in oxygen fugacity. So if mid-ocean ridge basalts show this very wide range, all the data throughout all time and all of these komatiites and pickrite lavas going back to the Archaean falls in the range of modern Morb. And so for me, we are looking at scatter through time and not a secular evolution in time. Again, because the oldest Archaean flows and all the Archaean data fall within the modern range. So in our review, we concluded that the oxygen fugacity of Archaean basalts, picrites, and komatiites can't be distinguished from modern Morb and OIB, and the proxies show a lot of scatter, and that there's no evidence from the rock record there that 3+ total has evolved since the Archaean. But there's a lot of additional lines of evidence that I think sometimes get forgotten that I want to bring up again for this group. We can look at the concentration of redox-sensitive cerium relative to other elements in the Hadean and in Hadean zircons. And what you're looking at here is this cerium, redox-sensitive cerium concentration against temperature, looking at 3 buffers, iron wustite, FMQ, same thing as QFM, and magnetite, hematite. Those are the 3 buffers we've been looking at this whole talk. And the lunar zircons record really reducing conditions, which we know took place during the magma ocean on the moon. But Jack Hill zircons, which are our Archaean zircons, are recording QFM. And so the point made by Trail et al. In Nature is that the earliest zircons, earliest crust was already oxidized, even in the Hadean. We can also look at the concentration of chromium, another redox-sensitive element, in mantle-derived melts and spinels through time. So here on the y-axis, I've got chromium in the melt as a function of MgO content in these spinel saturated melts. And you can see that at FMQ, the chromium concentration in the melt is lower than it is under more reduced conditions of the iron wustite buffer. Delano showed that the moons has these higher chromium concentrations, whereas mid-ocean ridge basalts fall closer to the QFM buffer. And then, really interesting, showed these Hadean pairs, showing that the Hadean overlaps completely with modern Morb, again, when we look at chromium in these melts. So we're having this approach of comparing experiments to natural samples. Same thing, Rawlinson in Lithos in 2017. That was a nice study where he looked at the 3+ to total ratios of chromites themselves through time. Sorry, flipping the axis on you here, like which way is today versus in the past. But again, looking at these chromites and not seeing any change from modern times. So we all these things that should be recording secular evolution are not. So these Archaean zircons, chromites, and the whole rock, chromium, vanadium, iron systematics all record oxygen fugacity of the modern mantle. Okay, and it's true that there's a lot of scatter. So, the main message here is I don't think there's any evidence in the rock record that 3+ to total has evolved since the Archaean. But we should look at basalts because basalts have gotten a lot of attention recently as well. Here's a classic paper, kind of started it all again in 2004, Lee and Lee, where they looked at mid-ocean ridge basalts are these circles, and the squares are Archaean basalts. And on the y-axis here is the vanadium-scandium ratio, which through a model, they relate to oxygen fugacity. It doesn't matter what the x-axis is here. This could just be a histogram. It relates to melt fraction, but it's not important for this conversation. What's important is that the Archaean basalts overlap entirely in FO2 space and vanadium-scandium space with Morb. And I want to draw your attention to what they even put in the legend here. It's so important. They said we're only looking at things with MgO between 8 and 12 weight percent. Why? It's a condition of using vanadium scandium. That's because vanadium scandium ratio changes during crystal fractionation. As basalts fractionate olivine, the vanadium scandium ratio goes up. So MgO is a nice proxy for extent of fractionation. I'm showing you here mid-ocean ridge basalts from the East Pacific Rise. I'm even showing you in these white circles with the cyan outline, those are all basalts from a single segment of a mid-ocean ridge, 9 north on the EPR. And you can see that the vanadium scandium ratio varies widely at a single segment of a modern ridge, and it varies very systematically with MgO content. And so I'm also showing you here average morb and primitive morb as defined in various studies that I've cited here. So to get around this problem, Lee and Lee said we're only going to look at things that are primitive with greater than 8% MgO. Why did they cap it at 12%? It's because when you have higher than 12% MgO, you're probably not looking at a mantle melt at all anymore. You're probably looking at something that is cumulate olivine. In other words, your rock does not represent a liquid. So that's why Lee and Lee, who came up with vanadium scandium as a redox proxy in the first place, said it had to be between 8 and 12 weight percent. The reason for this trend with MgO is that scandium is more compatible in olivine than vanadium. And there's other elements that have been tried. Ytterbium is much better. Ytterbium has very similar compatibility to vanadium. This is these blue dots again are mid-ocean ridge basalts, and we see vanadium and ytterbium regressing through the origin here. But for this study, for this review article, we said, well, what's the perfect element? And the perfect element we called V star. V star is a fictive element, and it's your scandium concentration and your ytterbium concentration combined such that vanadium star behaves exactly like vanadium in mid-ocean ridge basalts today, modern morb. Here we're looking at the EPR where we don't have any plume influence, very clean mid-ocean ridge. So vanadium star is analogous to vanadium scandium, only vanadium star eliminates this fractionation process problem. So here are the exact same data. I'm now plotting vanadium star against MgO for the same data, and we have no trend with MgO. This allows us to look at basalts with lower MgO contents than 8 weight percent, which is really useful if you study arcs, especially because really primitive arc samples are rare. And when we apply vanadium star globally, again, looking modern first to make sure, reality check or sanity check, vanadium star is 7 plus or minus 1 in the ridges. And at arcs, arc basalts have vanadium star of 10, 11, 12, 13, 14. About, 12 is very average. So if we look now back in time, we're going back in time again to the Archaean, and we look at basalts from ambient mantle or basalts from arc mantle. I'm taking those from the Condi study. So Condi looked at geological context to determine which rocks best represented mantle melts, and at geochemistry to discriminate between ambient mantle, like morb analogs in the past and arc analogs from the past. And when you apply vanadium star to this incredible Condi data set, and we added more data in 2022, you can see that there's no evolution in time. There's a lot of scatter, but vanadium star in these Archaean basalts is perfectly overlapping with modern morb. And the vanadium star of arc or arc mantle, as defined by Condi, also shows no evolution in time, but a tremendous amount of scatter today. And that point has been made elsewhere in the literature, that there's just a lot of scatter with these proxies once you start looking in the last 500 million years. Okay, but what about these eclogites, which are metabasalts? So eclogites that are in xenoliths, they've spent a really long time in the mantle, okay, billions of years in the continental lithosphere, but are metamorphosed from morb that has subducted. All right, and this is a really well-cited seminal work by Albach and Stagno in 2016. And what they showed is that these Archaean eclogites, shown here in red, record an oxygen fugacity that is lower than other metabasalts from ophiolites in more recent times across the GOE boundary. And again, these data are all included in this O'Neill and Albach review that I started the talk with. All these data are in here. What about these? Well, if I just plot the data straight from the supplement of this paper for these exact samples on our modern morb, they overlap. What I'm showing here are metabasalts, these Archaean eclogites that are older than 2 billion years old in pink, and ones that are less than 2 billion years old in green, and average morb, primitive morb, and the modern EPR are all there as they have been throughout this talk. And I think what you see here is that all the older metabasalts are really primitive. They have high MgO, and 3 of them have MgO higher than 12% and are probably not even representing liquids at all. And then you have these metabasalts that are included in the study that have less than 8% MgO. So their vanadium scandium is just going to be elevated just from olivine fractionation. So the only data that meet the criteria for using vanadium scandium are the 5 samples that fall between 8 and 12 weight percent MgO. And so I think what you see here is that all of these data from the Archaean fall on our modern morb trend. And what we've done is taken these exact samples, these same samples with the same filters applied, and calculated vanadium star. Sorry, I'm getting a little, hope that little reminder didn't pop up for you. These massifs, ophiolites, and xenoliths. Sorry, on this figure, old is on the left now, and today is on the right. Every journal seems to want that axis in a different direction. And we see no trend through time. All of them overlap with modern morb in this vanadium star space, and they overlap in vanadium scandium space. So what does it mean? I don't think there's any evidence in the rock record that the ambient mantle's oxygen fugacity or its 3+ to total ratio have evolved since the Archaean. And I just want to be careful to not say that they haven't evolved. It's that there's nothing statistically significant. We don't have the precision in our tools to see a trend through time because all the data from the past fall in the range of data from the present. The major implication is that shifts in mantle FO2 did not hasten or inhibit the GOE, and that as Dante Keneal pointed out in 1997, that evolution from core formation to modern FO2, modern 3+ to total in the mantle, happened very rapidly in the Archaean. And I think the big exciting effort in the field now is to figure out how that happened. In this review, we go over these 3 big categories of model, and this is like where I'm wrapping up here. Go over these 3 big categories of model for how you could oxidize very rapidly during the process of core formation. And I just, for this group, wanted to point out this is a very hot field, a lot happening. You can see here the 3+ to total ratio is a function of pressure. All these different curves, pink, gray, red, green, blue, are all recent studies. So this is highly uncertain at this time and is a big focus of the diamond cell community. And one final note that even though I've focused this talk on the rock record, I wanted to make sure that people understood, going back to the very thing I opened the talk with, that you can have, in this case, I'm showing an empirical model for solid peridotite with a 3 plus to total ratio of 0.03, a mantle 3 plus to total ratio. And oxygen fugacity can vary considerably depending on the mineral assemblage that is stabilized at different PNT with that same bulk ratio. So again, if I had one message for a redox curious community, it would be that when a study talks about the mantle being more or less oxidized, to lean into whether they're talking about a change in the redox budget of the mantle, a change in the 3 plus to total ratio, or if they're talking about a change in the oxygen fugacity due to a change in pressure or temperature. And this study that I'm showing here, this is from Bernard et al. 2024, where we're focused on the generation of melts in the garnet field as you decompress into the spinel field. But there are also a lot of papers that are talking about extracting melts from along this limb here, which I talked about earlier in the talk, the garnet olivine orthopyroxene assemblage, which gets more reducing as with depth as pressures get higher. And so as you decompress solid mantle, things could be getting more oxidized as you decompress and then turn over and become more reduced. And so you really have to look into the thermodynamic model details to know what's being referenced. Okay, that's it. And hopefully we have lots of time for questions.
All right. Thank you so much, Liz, for an excellent talk and taking the time to speak with us. We'll now open the floor for questions. If you'd like to ask a question, please use the raise your hand feature or feel free to type your question into the chat and I'll read it out for the group. We'll give people a second to come up with their questions.
Maybe I start, Liz, with a simple question while people coming up with their questions. So for vanadium star, do you know if there is any control by temperature or pressure, or would it be the same going back to Archaean?
Yeah, so that's a really good question. So we spent a lot of time on that in the paper because, and there's a great, just so I don't forget, and I could put this in the chat or someone else, there's a new paper out by Enrico Cacciatore about vanadium scandium and its lack of temperature dependence, no temperature dependence on that ratio. And that's exactly what we showed in this 2025 review. What we did is we looked at 1 atmosphere studies. And in 1 atmosphere study, you know the oxygen fugacity because it's recorded by the sensor that's right in the furnace. And you know it extremely precisely. And you know the temperature because there's a thermocouple right in the furnace. And the partitioning of vanadium ratio to scandium, they're both a little temperature dependent, but as a pair, as a ratio, they are not temperature dependent. And the same is true of vanadium star. So we looked at the 1 atmosphere experimental data, and I feel like I can say like with real certainty that there's no temperature dependence to vanadium star or vanadium scandium. Is there a pressure dependence? That's, we just don't have the problem when you start to look at pressure, like the Wang study did this in 2019. You have to combine 1 atmosphere data with piston cylinder data or multi-anvil data. And what all of these proxies are most sensitive to is oxygen fugacity. They're super sensitive to oxygen fugacity. So if you're using if you're using something, in a 1 atmosphere furnace, you have that zirconium sensor and you're measuring the oxygen chemical potential directly. In a solid media, large volume apparatus like a multi-anvil or a piston cylinder, you're using some sensor that's like nickel and palladium, or you're using the composition of the capsule, or you're using the 3+ to total ratio of the melt, which is pressure dependent relative to oxygen fugacity, and you're relating that back. And so if there's any systematic bias between your oxygen fugacity calculation at high pressure and 1 atmosphere, you could interpret that offset as a pressure dependence when it's just a systematic offset in your FO2. So I think any dependence on pressure, it remains an open question and one that will be very difficult to resolve. Although this Cacciatore study, I would keep an eye on that. I think there'll be more work coming out of that group.
Thank you. I have another question, but I let other people go first.
I'd say you're good for it, Andre. Or Alex has one.
Okay.
Yeah, thanks for that talk. That I really appreciated how you took the time to explain this mantle redox concepts at the start. It helped me a lot.
Oh, good.
So I was wondering if there's sort of a mass balance demonstration somewhere in literature that, like, if you started taking the oxygen fugacity of subducted sediments or subducted material and started mixing that with the mantle at, initiation of the GOE. From then to now, 2 to 2.5 billion years, how much would we expect to see? Are there calculations that demonstrate how much we would expect to see a change in this?
Yes. I'm going to give you the seminal references.
Okay.
Katie Evans. Katie Evans is the originator. She is the originator of the concept of redox budget, which has been really essential to the FO2 community because, again, you can add a lot of oxidized ingredients to a system and not move the oxygen fugacity because you're still buffered by the assemblage. You can also keep the redox budget the same and shift the FO2. So it's, she was the originator of the concept of redox budget with her seminal paper in 2006. But then the paper you're looking for is Evans and Tompkins, 2011. And she does the modeling where she looks at the mass balance of redox budget being subducted and says, okay, here's the mass of the slab. Here's the mass of these redox budget going down. Here's their oxidizing potential. Here's the mass of the mantle wedge. That's what you're looking for, right? Like a mass balance calculation, and shows that you cannot oxidize the mantle even with all of geological time through subduction. If you were to try to oxidize it uniformly, okay, and she's focused on uniform oxidation because the ultimate application would be, say, ridges again or something, right? But it is more nuanced. And so that was her 2011 kind of like, I would call like seminal breakthrough paper there. I think it's maybe in geology. And then what's happened since is, we think melting doesn't really work that way though, right? Melting is channelized. And when you subduct, you have flux melting, and where that water gets to is going to melt. And you have decompression melting and you have flux-induced melting. And you could have areas in the mantle wedge that are melting because they got wet and have subduction influence in their chemistry, adjacent to mantle wedge that is melting later because it's decompressing. And so an interesting study is Berner et al. 2017 in Tonga, where they've dredged the hanging wall, the subduction zone, and looking at the actual pieces of the mantle, you can see mantle that has melted due to decompression and mantle that is melted because of subduction influence. And you can see that in the trace elements of orthopyroxenes and the clinopyroxenes, very clear. And you can see that when the mantle melts because you've added subducting components or it's flux melting, the oxygen fugacity is higher. An adjacent mantle that hasn't had subduction influence records the same oxygen fugacity as Morb mantle. So I would start there with Evans, and she has continued to do amazing work on redox budget in the subducting slab. A really nice review paper in 2021, Evans and Frost, kind of revisiting that.
Got it. Thanks. So it's
Yeah,
like
and
they could be. Oh, sorry.
go ahead.
Oh, the fact that we're not seeing an expression of oxygenation of the mantle could be in part that you're stuck at a buffer, and it could also be in part that there's it's more heterogeneous down there than it
Yeah,
otherwise
I
a
think
fully mixed mantle. Sorry.
I think I'm saying something slightly different in this talk, which is that um, if we just the tools that have been applied to go back in time um, show the same overall spread back in time as when we apply those same tools to mid-ocean ridge basalts, say, dredged today, or ocean island basalts erupting today. And so you have there are fewer datums going back in time. And, is there a trend or is there not? I think the message is to say all the numbers going back in time overlap with their modern analogs. So I think it's hard to argue for secular change based on the data we have from the rock record. Now, there's been a lot of work recently, and I know there's many groups still working on this, is looking for secular change more recently in Earth history in arc basalts. So, okay, you guys agree that the GOE happened, right? And the ocean oxygenated to depth over time. Did that subduction influence the nature of arc basalts that came out the other end? There's the Stolper and Buchholz, Daniel Stolper and Claire Buchholz in 2019, that had data and discussed that. And then there's new data coming out that finds something different. There's just a lot of scatter. And so will we, it probably is going to require a very careful study where you are able to find some kind of natural laboratory to isolate the variables and see if you have a trend when you're not looking at like all the data in GeoRock, for example.
All right, cool. Thank you very much.
Yeah, so maybe I guess my second question or comment, sort of to rephrase your conclusions within precision of the method, we don't see a trend in mantle redox change through GOE, but on the other hand, clearly was very early in history a huge change in mantle redox, and when the question, what if this huge change didn't actually result in oxygenation of crust and atmosphere and ocean early on, should we expect it to have effect during the GOE?
During what? During
the GOE. So we had this large change in the Hadean, and apparently it didn't result in any oxygenation of atmosphere ocean. And when around GOE within precision we don't see change, or if it was very minor. So does it tell us that mantle redox didn't affect on oxygenation of atmosphere and ocean?
Yeah, I would say it didn't. I think, I'm just gonna go back uh, to these models. So what the planetary community is working really hard on right now is magma ocean atmosphere dynamics. So what would be the oxygen fugacity set at the surface of a global magma ocean in equilibrium with metal at its base? That's a very difficult experimental challenge. A lot of papers coming out about that. And then what would the chemistry of the atmosphere be at those ultra high temperatures? The experiments, we don't have experimental apparatuses that go to such high temperatures as we're expecting for magma oceans. So there's a lot of extrapolation. And then there's this coupled evolution as well, because if you're outgassing, say you're outgassing hydrogen, there's going to be this feedback too between building an atmosphere and what happens in the magma ocean. And so I think what you're saying is, all of these scenarios, like I'll just take even this first scenario here, results in a magma ocean with a gradient in oxygen fugacity, even though it's isochemical, the same 3+ to total ratio everywhere. So you're oxidized at the surface, or more oxidizing at the surface, and you stabilize a carbon monoxide rich atmosphere with carbon dioxide, but not oxygen, not O2. I think that O2, I would say the evidence points to photosynthesis, that points to life, and not O2 coming from the mantle on Earth. Of course, this is also interesting for the planetary community because you can imagine other planets with other initial 3+ to total ratios, other Fe, other metal oxide ratios that would evolve differently. And then, the perovskite, the oxygen pump, that's like the Wade and Wood model from 2005, where you generate perovskite and iron metal, and the iron metal, that's this scenario down here, the iron metal sinks to the core. The 3+ rich perovskite is left in the lower mantle, and like, what's the time scale over which you might expect that mixing? But again, these are all competing models for how you get the mantle from like QFM -5 to QFM, say, -1 in the Hadean. But what there doesn't seem to be evidence for is ongoing evidence in the rock record of evolution, like either steady or step function evolution after that time. Like the big step took place in the Hadean, not in the Archaean.
Yeah. And when it was 2 billion years, when sort of Mantle was in largely oxidized state, but it had no impact on atmosphere ocean between, let's say, 2.5 and 2.5.
Yeah, I don't think the mantle. I would say that the rocks that are the product of melting the mantle, that are the rocks that represent mantle melts, don't show any statistically significant secular change across that boundary. And that it's a separate question. The question of whether oxygenation of the atmosphere by life then influenced what erupts, say, from arcs, that's a separate question. And I think the jury is still out on that, and groups are very actively working on that, because you could generate oxidized arc rocks from serpentinization. Serpentinization, all you need is a mafic substrate and water, and you release hydrogen, you generate magnetite. You can oxidize the subducting slab without having oxygenated ocean bottom waters, without having an oxygenated atmosphere. So if we don't see any change in arc rock FO2 through time, it probably supports a mechanism for generating oxidized arc rocks that is inherent to processes of serpentinization. If we see a change in the oxygen fugacity recorded by arc rocks that happens after the deep ocean has oxidized, that points to a big role for subducted sediments, for altered ocean crust. And we definitely see a strong relationship in arc rocks between subduction influence and FO2. So really great studies that tie the oxidation state of arc rocks to sulfur derived from the slab. Sulfur has a lot of potential to shift, has a lot of redox budget because there's an 8-to-1 electron exchange with sulfur. There's good studies that show just bulk mass balance, nice correlations between fluid soluble elements like barium or melts of altered oceanic crust. There was just a paper, my group had a paper out just a few weeks ago on back arc basin basalts and looking at really nice correlations between melts, geochemical indicators of melts of altered oceanic crust and FO2. And it could be all of the above. It could be that that there's inherent, that melting of subducted lithosphere or contributions from subducted lithosphere are oxidized due to processes inherent, serpentinization, deserpentinization. And then on top of that, there could be boosts from subducted sediments that were oxidized on the surface. It could be both. I don't think we have all the answers yet, but there's a lot of papers coming out all the time on this topic.
Yeah, we've had a talk by Menk about a couple of 3 months ago about distribution of porphyry type deposits in arcs. And it seems like the majority of deposits after the HUE, but still there are few that go back to Archaean. And I think he involved sort of similar process not related to oxygen for oxidation, like serpentinization or something to do with garnet. Yeah.
So to get back to Alex's question, that distribution of porphyry copper deposits through time is exactly the motivation of the Evans and Tompkins 2011 study. That's their intro. They say there were no none of these porphyries back in time. There are today. Is that the Mantle playing a role? That's precisely the motivation of the mass balance study that I gave Alex the reference for. So that's a very long-standing observation. But that's the arc environment. And then so if in this talk I've been really focused on, I could give you a talk on this on arcs. This talk was really focused on ambient melts, melts of the ambient convecting mantle and Archaean rocks, not on the modern arc setting or arc settings going back through time. I would say there's a really interesting paper. Again, I'll give a shout out to Evans and Frost 2021, where they really interrogate the ability of serpentinization to release redox budget to the wedge, and kind of talk about all the other contributors of redox budget. I mean, it's hard work. It's like really careful petrography, right? Where they're, or like Jay Ague at Yale, really looking at these exhumed terrains. What are the minerals that are there? What oxygen fugacity do they record? Where are their stability fields? Where do we expect them to break down? It's hard petrographic work. I'd say.
Thank you.
I hope it's a plug for continuing to teach mineralogy and petrology to students.
All right. Any last minute questions? Oh, then. All right. Well, thank you for joining us today. Thank you for the wonderful talk. Next week we have Harry Sikos from the University of Petras, Greece, and we're looking forward to that one as well. So thank you very much.
Thank you. Thank you very much. I really enjoyed speaking with you guys. Contact me anytime. My email is easy to find. All right.